flight at steady speed, lift equals weight, and thrust equals drag. Lift and weight are about 8 times greater than thrust and drag, but for clarity's sake, we have reduced this ratio in the diagram. So we have two unequal pairs of forces acting at right angles to one another. But suppose we want to climb or descend. What happens to the forces then? As the nose pitches up, the picture changes. 3 of the forces, lift, thrust, and drag, are in the same relationship to the flight path in the climb as they were in level flight. Weight, however, still acts vertically downward, and so is now at an angle to the flight path, downward and backward. It is thus augmenting drag. This directional effect of the weight on drag slows the airplane down in the climb, so that both lift and aerodynamic drag are reduced. But if we add the drag effect of weight to the remaining aerodynamic drag, the total drag becomes greater than in level flight. To keep the forces in balance, thrust must be increased to balance the new force of drag plus its component of weight. Change from a climb to a descent, and weight, still acting vertically downward, is now augmenting thrust. The airplane will accelerate. Lift and drag will increase. So, to keep the forces in balance, we must reduce thrust to allow drag to balance the force of weight acting forward down the flight path. We can experience these forces physically by riding a bicycle up and down a hill. Going uphill, we must increase thrust to balance the proportion of our total weight acting backward down the hill. If we shed even a small fraction of that weight and deprive it of thrust, we can see what happens to it. Going downhill, the opposite applies. We have to reduce thrust to avoid excessive speed, and the discarded weight will continue forward down the slope. Once we leave the ground behind, however, no matter where we point the airplane, one of the 4 forces acting on it, weight, always acts in one direction, straight down. All the rest of the geometry of flight revolves around that central fact. And so, when we want to climb, we have to offset the effect of weight acting partly backward down the flight path by increasing thrust, just as we have to pedal harder to ride a bicycle up a hill. When we want to descend without increasing speed, we have to offset the effect of weight acting forward along the flight path and decrease thrust, just as we have to on a bicycle going downhill. Beyond a certain angle, the descending flight path becomes a glide. There is now enough weight acting forward along the flight path to keep the forces in balance, and thrust as such is no longer needed. Even in this situation, the forces remain in balance, and a steady speed is maintained on the glide path. But the proportion of weight acting forward along the flight path is now sufficient to act in place of thrust from the propeller and to equal drag. As soon as the airplane is leveled out again and power is restored, the 4 forces resume their normal pattern for steady level flight. In everyday flying, however, the airplane has to be maneuverable in all 3 dimensions. It can be deflected from straight and level flight in the pitching plane around the lateral axis, with nose lifting or dropping like this. In the rolling plane, with the wing tending to roll the airplane around its longitudinal axis. In the yawing plane, around the vertical axis. Or in any combination of the three. How can this capability be reconciled with a reasonable degree of stability in straight and level flight? Stability is a complex subject, but its basis lies in the plan form of the airplane and the arrangement of its flying surfaces. In the pitching and yawing planes, stability is assisted by the tail surfaces, exerting leverage along the arm provided by the fuselage. If we look at these tail surfaces, we find a horizontal tailplane and a vertical fin. Let's see how they help stability. To begin with, the four forces seldom act from the same point on the airplane. Weight is normally arranged to act from a point ahead of lift, in such a way as to create a nose-down moment around the lateral axis, so that when power is reduced, the airplane will pitch nose down. As it does so, the download on the rising tailplane will keep the airplane in a stable descent at a stable speed and under normal control. But no matter how stable the airplane, the air it flies through is often unstable. Local changes in pressure and temperature cause gusts and currents, which vary the speed and direction of the relative airflow, vertically as well as horizontally. They can thus cause local variations in the angle of attack. When a gust causes a pitch-up moment about the lateral axis, the angle of attack increases momentarily, and so does lift. But inertia, the tendency of an object in motion to keep on going in the same direction, will prevent an immediate change in its flight path. Meanwhile, the tailplane experiences an upload, levers the tail upward, and slightly overreacts. The airplane is now slightly nose down. The tail now reacts in the opposite direction, and through several brief oscillations damps out the disturbance, and the airplane returns to level flight. A gust striking at an angle to the flight path can make the airplane yaw about the vertical axis, and here the vertical fin comes into play. As it swings out, the airflow provides an opposite reaction to the action of the gust. And once again, oscillations will occur before the fin succeeds in damping out the disturbance. Gusts also disturb the airplane around its longitudinal axis by varying the angle of attack as between one wing and the other, and causing it to roll. In this case, the stabilizing influence is that a change of incidence affecting the two wings. The wing that is dropping experiences an increase in the angle of attack, and thus an increase in lift. This will stop the roll, but will not level the wings. At this angle, total lift, at right angles to the wing, is acting slightly in the direction of the roll, while weight acts downward through the center of gravity. The airplane therefore moves in a side slip in the direction of the roll. In a high-wing airplane like this one, the roll and slip is largely corrected by the effect of having the fuselage below the wing, and this will help the pilot to level the wings. In the same situation, a low-wing airplane relies more on the angle at which the wings are inclined to the horizontal, known as the angle of dihedral. When the airplane rolls, lift increases on the descending wing and decreases on the rising wing, so the roll stops. Lift is now acting slightly in the direction of the roll, and weight acts downward, so the airplane side slips. Thanks to the dihedral, the relative airflow now strikes the lower wing at an angle of attack greater than that at which it strikes the upper wing, which will be slightly blanketed by the fuselage if the side slip persists. Once again, the pilot must correct the slip and level the wings. No airplane is fully stable laterally, and if an involuntary roll of more than a few degrees is left uncorrected, the lift from that powerful wing acting at an angle to the airplane's path will pull it into an unstable descending turn. To recover from it, we must use the controls. The controls of an airplane enable us to maneuver it accurately and safely under all normal conditions of flight. Control is achieved by moving hinged surfaces on the trailing edges of the tail and the wingtips. The elevator attached to the tailplane, the rudder to the fin, and the ailerons to the wingtips, all of them operated by controls in the cabin. Moving the control column backward and forward raises and lowers the elevator. Pulling it back raises the elevator. Pushing it forward lowers it. Turning the wheel operates the ailerons at the wingtips. With the wheel to the right-hand aileron is raised and the one on the left is lowered, rolling the airplane to the right. Turning it in the opposite direction moves the ailerons in the opposite sense and rolls the airplane to the left. The rudder is controlled by pedals. Pushing the left-hand pedal swings the rudder to the left. Pushing the right-hand pedal swings it to the right. Each control can be operated separately, or they can all be used in coordination when the maneuver demands it. In the smoke tunnel, we can see how they produce their desired effect by deflecting the airflow. When we lower the elevator, the airflow is deflected downward, and this increases lift on the tail. When we raise it, the airflow is deflected upward, and the tail receives a download. The effect is to rotate the airplane around its lateral axis. The rudder works in just the same way in the vertical plane, with the airflow deflected to the right or left, so as to push the tail in the opposite direction, swinging the airplane around its vertical axis. The ailerons deflect the airflow in the same way, but in opposition to one another, lowering one wingtip and raising the other at the same time, controlling the airplane around its longitudinal axis. The remaining primary control is the throttle, which enables the pilot to control thrust. To increase power, the throttle is pushed forward. To reduce power, it is pulled back. Let's see what happens when we use the controls to change the flight path, or simply to take off and climb. The pilot opens the throttle, and the airplane accelerates. As flying speed is reached, he pulls the control column back. The elevator rises. The tail goes down. The airplane lifts off and rotates into the climb. The elevator returns to the neutral position. What the pilot has done is to increase the angle of attack so as to give the wing the extra lift it needs as the airplane rotates. Now let's look at the whole sequence in animation. The airplane accelerates to flying speed. The four forces are now in play. To rotate the airplane, we must put a download on the tailplane by raising the elevator. The angle of attack on the wing increases as the tail goes down, and lift becomes greater than weight. Once established in the climb, the elevator returns to neutral. Lift is reduced to balance the component of weight acting at right angles to the flight path, and thrust must be increased to balance aerodynamic drag plus the component of weight acting backward down the flight path. So the controls are used in this case to change the flight path from level to climbing flight by a controlled increase in lift at rotation. To level off, the elevator is used in the opposite sense, to lift the tail. And thrust must be reduced to allow the airplane to remain at a speed where lift exactly equals weight. To descend, the elevator is again lowered, and the tail lifts. And thrust must again be reduced to take account of weight acting forward down the flight path. At the controls themselves, only very slight movements are required to deflect the control surfaces sufficiently to change the angle of attack and thus increase or decrease the amount of lift from the wings relative to weight, while the throttle is used to maintain the balance of thrust and drag. Going round corners, racing cars depend on their road-holding capabilities to prevent them being hurled outward off the track by centrifugal force. If we try to turn an airplane with rudder alone while keeping the wings level, centrifugal force will cause it to skid sideways. On a bicycle, centrifugal force will throw us off unless we counteract it by leaning inward toward the center of the turn. And so we bank the bicycle in the direction we want to go. We need turn the handlebars only slightly in the direction of the turn. So it is with the airplane. Here it is lift that provides the principal turning force. We have only to bank the airplane slightly in the desired direction, and even a small proportion of lift acting toward the center of the turn is powerful enough to pull the airplane in that direction. This means that lift has a double part to play in the turn. As we bank into the turn, lift acts partly into the center of the turn to counter centrifugal force, and partly vertically upward to balance weight. The airplane turns. If we increase the angle of bank to make a steeper turn, a higher proportion of lift acts toward the center of the turn, and the proportion of lift still acting vertically is no longer enough to balance weight. So we must increase the sum total of lift, first by tightening the turn and so increasing the angle of attack. But this will also increase drag. So to balance it, we must increase thrust. Lift and weight are now in balance. And so, to control the airplane in the turn, the pilot first applies aileron and a little rudder. In a steep turn, the pilot increases the angle of attack by gradually pulling back on the control column and opening the throttle to increase thrust, so that the vertical component of lift still equals weight. Then, when we come out of the turn, we reduce both angle of attack and thrust to their normal values in straight and level flight. we can turn in a glide. Or we can turn in a climb, so long as we use the controls to give the airplane the extra lift it needs in the turn. The twin-engined airplane differs from the single-engined in several significant ways. The most important aerodynamically is the way in which thrust is usually divided by mounting the engines on the leading edges of the wings, on either side of the fuselage. This has the effect of directing the slipstream of each propeller over the wing itself, thus augmenting lift over a considerable proportion of its span. This means that the pilot can use the throttles to accelerate air over a part of the wing, and thus increase lift, controlling the attitude of the airplane in pitch, and changing or maintaining height with very little variation in speed. However, there is always the possibility that an engine may fail. When this happens, total thrust and slipstream are lost on the affected side. Unless we prevent it, the airplane will yaw toward the dead engine. And the wing, having lost some of its lift and now slowing down in the yaw, will drop. To straighten up the airplane and restore lift to the affected wing, the pilot must apply rudder against the good engine and hold it there until he can make a safe landing. To do this, he needs help. The way in which a displaced control surface can be held in position against a considerable aerodynamic force is by means of trim tabs. These are auxiliary surfaces fitted to the trailing edge of a main control surface and working in the opposite sense. Thus, a rudder trim tab applied to the right will hold the rudder to the left, and vice versa. Trim tabs enable the pilot to correct and hold any normal variation in the trim of the airplane without having to hold the control force physically. Elevator trim tabs enable the pilot to trim the airplane in the pitching plane, and these work in the same way as the rudder tabs. Downward to raise the elevator, upward to lower it. These can be used to correct variations in the position of the center of gravity. The total weight of an airplane acts through a single point, known as the center of gravity. The designer tries to put the center of gravity a little way ahead of the center of lift of the airplane, so as to give the pilot better control. This is compensated for by fixing the tailplane at a lower angle of incidence than that of the wings, so as to give it a download. But the loading of the airplane can change this relationship. An extra load placed behind the center of gravity will move it back to a point only just ahead of the center of lift. The airplane will now tend to pitch nose up. So we must trim the elevator to reduce the download and bring the airplane back to level flight. The airplane can thus maintain level flight despite the fact that the center of gravity is misplaced, provided it is still within the design limits of the airplane. and without the pilot having to hold the airplane level manually. In the same way, if we need to increase the download on the tail, we can use the trimmer in the opposite sense. The controls give us command of the airplane. They allow us to use the forces acting on it, to balance them as we choose, and to control the pressure pattern around the wings as they move through the air, so that we can fly and enjoy the airplane to the limits of its performance.